Welcome. I'm Elizabeth Stage, and I'm the director of the Lawrence Hall of Science, and I'm very honored to be hosting this event in honor of Charles Townes and the laser and all the exciting things that have happened in the last 50 years. And without further ado, it is my distinct pleasure to welcome Frances Hellman, the chair of the physics department.
So, good afternoon and happy 50th anniversary of the laser. So this is officially the 50th anniversary of the first working laser, and I'm really delighted to see so many people here to celebrate LaserFest. I want to say a special welcome to those of you who've come from far away, former students of Charlie Townes and even former colleagues who were with him at Columbia when he had his eureka moment, which I believe we're going to hear about later today. So the physics department and the Lawrence Hall of Science is extremely pleased to be producing what is pretty much the first laser event of 2010, part of this this year of the celebrating the laser. And we are even more pleased to be able to do this in honor of Charlie Townes. Charlie has made the University of California his home since 1967, and we're very proud of all of his accomplishments, and we're very proud to be able to assume bragging rights for every discovery he has ever made. Something that you just take on as, you know, when you, as one of my pleasures as chair to have him in my department. So what better way is there to honor Charlie than to have him speak for himself? Today you're going to hear Charlie about how some discoveries happen. You will also learn about the present and the amazing future of the lasers from our own professor and director of the Advanced Light Source at LBNL, Roger Falcone, and from our distinguished alumnus, Robert Byer, a professor at Stanford and a newly elected vice president of the American Physical Society. Last, we're going to hear from Dr. Ed Moses of the National Ignition Facility at Lawrence Livermore National Laboratory, who's going to introduce a 3D video about the National Ignition Facility known as NIF and its phenomenal use of lasers, which is the moment when you'll get to put on those 3D glasses you've all been given. So he'll tell you when's the right moment to put those on. There's a lot of people I want to thank for putting this event together. First of all, NIF, I want to thank Ed and his incredible group who contributed tremendously to the exhibit that hopefully some of you had a chance to see upstairs and over the weekend. There was some 1,500 kids and parents who came to see this exhibit. There was Erica Friesen and her cohorts at the Lawrence Hall of Science, and we really want to thank them for hosting the event and guiding us in the creation of this science exhibit for kids. It's something that's been a lot of fun for the department to join with the Lawrence Hall of Science to do this. There are also a lot of really great graduate students from the physics department who gave their time to come up and help expose all these kids to this exciting branch of science. Finally, we want to gratefully acknowledge the Optical Society of America and the American Physical Society who awarded us a grant that helped make the exhibit upstairs possible. And for those of you who did not yet see the exhibit, you'll have a chance after, during the reception and after the talks. Now I'm going to turn the platform over to an image of Chancellor Robert Birgeneau, who recorded this message for Charlie because he couldn't be here. And after that, so I will turn to the message from the Chancellor.
Hi, Charlie. I must say I'm so sorry that Mayor Catherine and I cannot be at the event celebrating all of your wonderful work. But we're in Washington, actually, working on behalf of the university and working the offices in DOE and in Congress. I must say that both Mayor Catherine and I feel that one of our great privileges in coming here to Berkeley has been to be able to become friends with you and Frances. You're two of the most wonderful people we've ever met. Of course, you set such a standard for all of us physicists. I realized that now you have indeed matched Hans Bethe with 7 decades of Nobel Prize level physics. This is just extraordinary. Furthermore, last Saturday I was driving by and it was about 8:30 in the morning, and there you were going into the lab at 8:30 in the morning on Saturday. What an example for all of us. Of course, we cannot imagine the modern world without lasers and lasers, and so the work you've done has had such an impact on the whole world around us. Look at CD players, DVDs, almost everything one can imagine. The world was changed by the research you've done. And of course, you've also profoundly contributed to our understanding of the universe through your work in astrophysics. So Charlie, congratulations. And I just want to say I'm really glad that we're having this day to honor you. I'm really sorry that we cannot be there to co-celebrate it with you, but I'm sure we will have an opportunity in the future. So again, congratulations to you, and of course to Francis, rivaling Mary Catherine as among the best waggies in the world. Thank you.
So in the interest of complete clarity here, I want to make sure everybody understands it is Francis Townes that the Chancellor is referring to. Who wears many distinguished hats herself. So without further ado, let me turn the podium over to a distinguished Professor, Charlie Townes.
Oh, thank you. I'm just so delighted with this occasion. See so many of my friends here, many of whom have contributed very importantly to the field of optics that we're talking about. Old friends in science and other things. And it just makes a wonderful occasion. I appreciate your being here. We are celebrating really a long history of developments in optics, of lasers and in optics and so on, contributed by many people. This field has grown as a result of many, many contributions. That's typical of science. It grows as a result of many people's contributions and of different kinds that add on, and it grows. And that's great. It's important to humans, and let's keep going. Now, I'm going to talk about how discoveries happen. They happen in many different kinds of ways. Some of them are quite accidental. For example, I was at Bell Telephone Laboratories when the transistor was discovered. The transistors made an enormous difference to us. And how did it happen? Well, a good friend of mine, Walter Bratton, he was trying to measure the resistance of copper oxide on a copper wire. And he kept making measurements. He was very puzzled about it. And he got some results that he just didn't understand. So he took it into John Bardeen, a theorist, another good friend. Took it to John Bardeen and said, you know, what is this? What's going on? And John looked at it and studied. Says, hey, you've got amplification. Oh, amplification. Let's figure that out. And so they did, and then their boss, Bill Shockley, another good friend, Bill Shockley jumped into the business. Oh, he wanted to be part of it, and he was. And he picked it up and did some more things with it and so on, and there was a transistor, and you know what it's done for us. Accidental discovery, but as a result of careful examination of some results, measuring results carefully, thinking about them, saying, oh, this is something peculiar, this is something new, I don't understand it. And then with John Bardeen, they understood it. Now, I also mentioned the Big Bang, discovery of the origin of the universe. Arno Penzias, I'm delighted to say, is with us here. And Arno was one of my previous students, but he went on to Bell Labs, and with Bob Wilson, they were looking very hard to see some radiation, and they had built a good maser amplifier, which was more sensitive than other amplifiers at the time, and to look at this radiation coming from interstellar space. They looked, they saw something that was surprising. They recognized it was surprising. They saw some emission coming from space, more than they expected, and it came from all kinds of directions. That was the discovery of the origin of the universe. What could be more important? The thoughtful, careful examination that they made, they recognized it was something new, and it was. What could be more important? Arno, would you stand up? Ah, I know. Where's Arnold? Well, now, then some discoveries, some important discoveries come about just from very careful, very careful measurements, very precise measurements, very careful measurements. You measure something that's supposed to be known and measure it more precisely than anybody's done. Sometimes you find out something surprising. For example, Willis Lamb, who was at Columbia with me. Willis Lamb measured the fine structure of hydrogen. It wasn't quite what people expected. It was a new discovery. New discovery, new effects. You know, so he got a Nobel Prize for it and so on. Just very careful measurements. And many things come about that way. New discoveries also come about from careful searches, purposeful searches. There are many important things to be searched, we know. And many things that may not seem important, we search them carefully, and something new may turn up. But be sensitive to those. Now, what are some of the things we want to search? Of course, dark matter, for example. What in the world is dark matter? Dark matter is most of the matter in the universe, and we don't know what it is. Well, everybody should think hard about how to find out what is dark matter. I hope somebody will find out. And of course, there will be many thoughts, many careful thoughts, many careful experiments. Try to figure out what is dark matter, for sure. Well, now, the maser and the laser came about, in a sense, from a search. I'd been working in microwave spectroscopy using normal electronic oscillators, and we could get down to wavelengths of half a centimeter or so. And there's a lot of exciting spectroscopy to be done there, high precision with good oscillators. I wanted to get down to shorter wavelengths. And I tried and tried. I looked all around how to get anything. Was anybody making anything with shorter wavelengths? Well, you could get maybe a few harmonics, but not much. And how could we get shorter wavelengths? Well, I worked on it. The Navy was supporting my work, knew I was working on it, and said, well, look, we're interested. Would you form a national committee to examine how to get to shorter wavelengths? We were thinking of getting on down to a millimeter or half a millimeter, or even a quarter of a millimeter. Wow. How to get to shorter wavelengths? Well, okay, so I formed a national committee of very important people, engineers and scientists. A very important committee. We traveled all over the country. We traveled abroad, examined, did anybody have any ideas how to get to shorter wavelengths? And looked at everything. And after about a year's time, decided, well, we just haven't found anything. We'll write a report saying, well, we haven't found any answer. So we met in Washington to write this report, a final report saying, sorry, no result. And just before the meeting, I waked up early in the morning worrying about it. Why hadn't we been able to find anything? And it was a nice bright morning. I went out and sat in the park on a park bench. Thinking, now, why hadn't ever been able to get an idea how to get to shorter wavelengths? And I went through all the things I'd tried and said, well, this doesn't work and that doesn't work and so on. I had tried things with my students, had tried some things that didn't work. And well, of course, molecules and atoms can produce short wavelengths, but they can't amplify. Well, now wait a minute. If in an excited state, you can stimulate them, they give energy. Oh, wait a minute, they can amplify. Now, but of course we can't make them, well, let's see, how can we do that? Well, I was at Columbia University where Robbie and Cush were working on beams of molecules and atoms and separating them into different states. And I said, oh, well, maybe I can separate them. Maybe I can get more in an upper state than a lower state and get some amplification. And I pulled out a paper and pencil, and I knew all the numbers, and I figured out, oh, it looks like probably could do it with ammonia or something like that. Looks like the numbers probably work. But it was so uncertain, I didn't mention it to the committee at all. So the committee, we went ahead and wrote our report, so we don't have any answers, sorry. And I went home and I wrote down my notebook, figured it out some more. You know, it looked like it really would work. Well, I persuaded a graduate student, Jim Gordon, to try it out. He had been working with beams before, molecular beams, and as an undergraduate, and I persuaded him to try it out. He was willing to try it, and he worked on it for about a couple of years. And then Professor Robbie and Professor Cush was then chairman of the department. Robbie was previous chairman of the department. Both of them, of course, have Nobel Prizes. Very excellent physicists. They came into my laboratory and said, look, Charlie, you've got to stop. That's not going to work. We know it's not going to work. You know it's not going to work. You're wasting the department's money. You've got to stop. Unfortunately, I had an associate professorship by then. They couldn't fire me. Even the chairman of the department couldn't fire me. No, I think it has a chance. I'm going to continue. Oh, they marched out of my laboratory angrily and so on. Well, about 3 months later, Jim Gordon dashed into my class where I was teaching. He said, it's working, it's working. And so we all marched out and went up to see this thing working. Now, show you, you see, we've been working on it about 3 years. A lot of people came to our laboratory and visited. Oh, yes, well, that's interesting, but nobody competed. New ideas are new, and a lot of people don't believe them, and why bother? Well, we've all got to think hard and try new things. Nobody competed with me at all for those 3 years until it was working. And once it was working, then everybody got excited. Everybody got excited, and there was a big field, and everybody jumped in the field. On the other hand, shortly after that, I was walking along a street in Denmark with Niels Bohr. And he asked me what I was doing. I told him about, well, we had this new oscillator, molecular oscillator, which gave very, very pure frequency and so on. And well, he looked at me and said, oh no, that's not possible. No, you misunderstand something. You misunderstand. No, we have it. No, that's not possible. I suspect he was thinking of the uncertainty principle. You send one molecule from here to here on a short time, you can't make a very pure frequency. I suspect he was thinking of that. He didn't tell me what he was thinking of. He said, no, you just misunderstand. But of course, many molecules are different from a single one. And so he never believed me. Other people had doubts too. John von Neumann doubted, oh no, that can't be right. Well, he went off and got a cocktail and came back to me and said, hey, you are right. Tell me all about it. So he recognized it. But you see, these are new ideas. New ideas are surprising, and we've got to be open-minded. We've got to work hard. Now, we built this first maser. It worked. Became an exciting field. Nobody thought it would get much shorter wavelengths. Oh, yes, it's nice. Microwaves, they make microwaves. And nobody tried to build a shorter one. But that was my primary purpose. I wanted to get on down the infrared. I tried to make it work in the microwave region first, just to make one work. And then I said, well, if it works, then we can get on down to shorter wavelengths. So I wanted to get down to shorter wavelengths. Get another beam of molecules, maybe, that could produce shorter wavelengths. Well, finally, in 1957, I sat down at my desk and I've got to figure out what best to do to get down to shorter wavelengths. And I started writing down the equation, thinking about it. I say, hey, wait a minute, looks like we can get right on down to visible light. Wow. Well, now, by then the field was a hot field, and I knew I shouldn't talk about it. Everybody else would jump into it and compete with me. But I was consulting at Bell Labs, and Art Charlow, who had been a postdoc with me, was there. He had been a postdoc, married my kid sister, and we were good friends. And so I went and talked with Art, and I told him, "This is looks like we can get down to wavelengths as short as light." He says, "Oh, that's very interesting. You know, I've been wondering about that. Could we work on this together?" I said, "Sure, of course." And so we worked on it together. And Art provided the additional idea of having two plane parallel mirrors. I was thinking of using a cavity for light. The cavity in the light would bounce all around. Two plane parallel mirrors, light bounces straight back and forth. Why did he think of that? He had been doing spectroscopy using parallel mirrors where you can do spectroscopy at very high resolution. You see, different fields add to what's there. And the interaction of different fields is very important in the growth of science. And the fact that I had studied engineering at Bell Labs before going to Columbia and having this idea, the fact that I studied engineering was a great help, and part of the reason I could match engineering and physics. Engineers couldn't match physics, how molecules and atoms behave so well, and the physicists didn't think in terms of oscillators and didn't match with engineering. And so that mixture of fields for me was a very important one, how new ideas are coming about again. Art Charlow and I thought about it and worked it out, and we kept very quiet about it because we knew there'd be a lot of competition once we said anything about it. It was a field of masers, was a very hot field then. And so I said, well, I guess we ought to give the patent to Bell Labs. You go take it to Bell Labs patent lawyers and have them patent it, and then we'll write a paper about it, publish it. So he took it to Bell Labs patent lawyers. He called me up the next day. He said, well, they say they don't want to bother to patent it. I said, why not? As they say, well, light's never been used for communication, and so Bell Labs is not interested. And they told me, if you want to patent it, you and Townes just patent it together and it'll be your patent. I told them, look, you know, they just don't understand. Just because they don't understand, we shouldn't cheat Bell Labs that way. You go tell them that, yes, it can be used for communication. So he called me up the next day and said, well, they say, okay, if we can show how it can be used for communication, they'll patent it. Reluctant approval on their part, but I said, okay, fine. So we wrote it up, and they made a patent saying optical masers and communication. Now, we called it optical masers. My students, after the ammonia maser came along, my students and I sat down at lunch, tried to figure out what to call it. And they helped pick out the word maser for microwave amplification by stimulated emission of radiation. You stimulate the molecules to give radiation. Microwave amplification by stimulated emission of radiation. That was the word maser. So when Art Charlow and I wrote this paper, we called it optical maser. And of course, very shortly after that, it was called a laser for light amplification by stimulated emission radiation. Same name, really, but for light. And of course, we also have erasers, infrared amplification by stimulated emission of radiation. But we don't use that name for obvious reasons. Erasers are really lasers. Infrared is still a laser. And all wavelengths except the microwaves are lasers now, but the microwaves, they're masers. But they're, of course, the same things. Well, we wrote the paper. We knew, because of competition, we better write a theoretical paper rather than doing experimental work on it, because if we did experimental work, people would come in our lab and then they would compete and so on. And so, okay, we'll write a theoretical paper on it first. And we did that and sent it in for publication. I immediately started trying to work on it. On the other hand, I'd agreed to go down to Washington for a couple of years to try to advise the government. And I knew I couldn't work very intensively, but I had my students working on it, and they started working on it. And we would try to build the first one. We did try to build the first one, but we didn't build the first one. The first one, of course, was built by Mayman. Ted Mayman, in industry. He was at Hughes, and he built the first one. And he had the idea of a flash lamp being an enormous amount of power instantaneously to excite things and produce a ruby laser. Well, that flash lamp hadn't occurred to me. It occurred to him. He'd been working in a place where there were flash lamps, and he saw how to do it, and he built the first ones. And that was the laser. And of course, that hit the newspapers, and wow. And all kinds of people were working on it by then anyhow. And all the first lasers were built in industry. Because the maser had come along, industry suddenly saw the importance of spectroscopy in fields like that. So they hired students that I and many others in the field had hired, had trained, hired students. So there are many students in industry who had the background. So all the first lasers were really made in industry. The next one was a solid state semiconductor laser built by Stevenson and Sorokin at IBM. And then the next one, which was a first continuous laser, was made by Ali Javan, who'd been one of my students, and Bill Bennett, who'd been at Columbia also, and Don Harriott at Bell Labs. And they made the helium-neon continuously oscillating laser, of course much weaker power than the pulse lasers, but still very important and very pure frequency. Well, now, of course, this became enormously important industry, and you know how it's grown. And so many different fields have contributed to it, and so many different people contributed to it. I can tell you, when after the first MESA, I went to Paris, and where Arnold Honig, one of my students, was working there, and I worked with Combrisson, and they were working on electron spins, and they'd found they could put electron spins in upper state and have them last a long time. I said, hey, wait, maybe we can make an electron spin MESA. Oh, and so, yes, that was it. And so that was the next MESA, and that was a tunable MESA, you see. So that field. Then I went to Japan and talked with a theorist, a biologist who had been working on the fluctuations in population. As people die and people generate, hey, wait a minute, that's just like the fluctuations in a MESA amplifier, excepting it doesn't have spontaneous emission, but otherwise just like, let me see those equations. And so that, my friends in Japan and I worked out first theory of the fluctuations in MESA and, of course, the laser amplifies the fluctuations. Came from biology of all things. Interaction of fields, very, very important, how fields contribute. Well, now, let's just look back now at the importance. How is it new discoveries and new come about? Well, of course, very important is hard work, devotion, thoughtfulness and hard work. That's true in all of these discoveries I mentioned. Those things had occurred. But they can come about, in a sense, by accident, quite completely unexpected. But we must look hard, look at new things, try new things, measure present things carefully, see what they're like, be very sensitive to any unknown phenomena, have a breadth of contact with various fields, be open to new ideas. And of course, some new ideas come from very hard, specific search, as the MESA and the laser did. Very specific search, but from the interaction with different fields also, that added to that and allowed them to come about. So you see, general exploration, very careful and thoughtful examination of what you have. You may be just looking at ordinary things and, hey, wait, there's something special there, something different I don't understand. Let's see. Or you may think hard about it and have an idea. Or you may think hard and try some things, and some of them don't work, and then suddenly some will work. So there are all kinds of ways. We must be open-minded, we must explore hard, be devoted, be insistent, and it's tremendously interesting. It's just great fun. Science is the most fun. I've never had to do much work, just have fun. Thank you all. I'm so appreciative of all you people. Many, many of you have contributed importantly to this field and contributing to other fields, and just great. And here we are in the interaction between scientists and the changing of ideas and adding of ideas. That's part of the great fun. Thank you.
Thank you, Charlie. That was actually quite inspirational. So we'll all go back to our laboratories and keep hoping for these moments, our own eureka moments. So I'm going to turn the stadium, I keep saying stadium, turn the podium over to my colleague, Professor Roger Falcone, who is both a professor in the physics department and director of the light source at LBNL.
Thank you, Francis, and thank you, Charlie. I want to start off from Charlie's paper in 1958 and jump forward to things that are happening now and will be happening 10 or 20 years in the future. So talking about the future of lasers, talking about things that Charlie was predicting and talking about how hard they would be. My slide on the first thing just shows the first maser, I think, of their ruby laser, something near and dear to Charles's heart, using lasers in astronomy, guide star work. What I'm holding in my hand now, the laser pointer, and here's the X-ray laser that I'm going to be talking about today. So there are some things that refer to things that happened 50 years ago and then today. So the outline of my talk is to take a look at Arcello and Charlie's paper in 1958, how it laid the groundwork for the optical laser, and it followed up on Jim Gordon and Charlie's paper on the microwave maser in not 1995. Sorry, you know how that snuck in there, back in 54. Yeah. So jumping forward to the X-ray and the first laser, some proposed uses of an X-ray laser, and then something about what's next. So the paper in 1958 to which I refer is the Charles Townes infrared and optical masers. And I just took a little look at the first paragraph here and pulled it off on the side here. I'm going to be talking about how we extend the infrared, the microwave maser into the X-ray region of the spectrum. Charlie was thinking about how to extend it into the infrared and the optical. And what he said was, as one attempts to extend maser operation towards very short wavelength, meaning infrared and optical, a number of new aspects and problems arise which require a quantitative reorientation of theoretical discussions and considerable modification of the experimental techniques used. And the fact that it took 50 years to get an X-ray laser is testament to this statement, or proof of this statement. If we go down in the paper a little bit later, and there's a summary at the end, summary of high frequency limits, meaning short wavelengths or high photon energy. Again, I pull out a section of the paper over on the side. He says, power in the spontaneous emission varies rapidly with frequency, as a power of frequency nu, as nu to the fourth or nu to the sixth, depending on the broadening mechanism for the laser. Charlie pointed that out. So we had a quantitative statement of how hard it was going to be. If we had to go up a factor of 10 in frequency, it was going to be 4 to 6 orders of magnitude harder to make the laser. More power needed to do it. And it becomes very difficult. And that means milliwatts in the microwave is the amount of power it takes to make the laser, meaning that it takes watts in the ultraviolet to make this work. And again, the statement here, masers cannot be pushed to wavelengths much shorter unless some radically new approach is found. And the radical new approach is what I'm going to be talking about today. What did it take to actually get to the X-ray region to make X-ray lasers? So brief physics, lasers sometimes are characterized by 3 energy levels. We can think of this as buckets, some on the ground, some high in the air, and raising water, filling the upper bucket. Energy levels are something about lasers are made. And to make a laser, we take a population, atoms in excited states from a lower state, and we put them in the upper state. We call that a pump. And then what happens is the lasing then happens between 2 energy states of an atom, and that's at some frequency nu. And it's this nu that Charlie was talking about. As we try to make that nu higher and higher, things get harder by 4 to 6 orders of nu to the fourth or nu to the sixth power. And the problem is that there's spontaneous decay, and Einstein told us about both these processes of stimulated and spontaneous decay. But the spontaneous decay is what hurts, because as we make these states farther and farther apart to get to shorter and shorter wavelengths, the upper state decays faster and faster. It's as though the bucket that you had up high here had a bigger and bigger hole, and things fell out of it faster and faster. So it's hard to put atoms in these states. So just to summarize it, for a maser, I just kind of made up these numbers from things I pulled out of papers, but they're roughly right. The density of molecules might be about 10 to the 16 per cubic centimeter, and the energies associated with this, if we put them in terms of a temperature, might be something like 100 Kelvin. To make an optical laser, oftentimes optical lasers are made out of solid state material, and I think Ed Moses is going to tell us about solid state lasers at Livermore that maybe had an excited state density of maybe 10 to the 19 atoms per cubic centimeter, but the energy has to go up a lot, maybe electron volts of energy, or 10,000 degrees, the temperature of visible light. For the X-ray lasers, the density of electrons, we make them using free electrons, turns out to be about the same, about 10 to the 19 every cubic centimeter. Okay? But the energy has to be much, much higher. Okay? Put it in terms of temperature here, it's a lot. But it's, so the power associated with it, we could say, moves from microwatts to watts to gigawatts of power needed to be put in the system. And it's that scaling, that amount of power that has to be put into a lasing medium, it's why it took 50 years to have happen. We went from microwatts to watts to maybe gigawatts of power here. Okay, so what are X-rays? Just one slide on what X-rays are. You know about the frequency spectrum, the electromagnetic frequency spectrum, radio stations, microwaves down here in frequency units or energy units, gamma rays up here in very high energy, very high frequency. The little portion of the spectrum we see with our eyes and the optical. Lasers, one thinks about across this whole electromagnetic spectrum. And why do we think about that? Well, why do we think about X-rays? We think about X-rays because they help us to see the invisible. They help us tell where atoms are placed in things like crystals and in solids and in molecules. We can use X-rays to see where are the electrons, not only where the atoms are in systems, but where electrons are and where their spins are if we're worrying about magnetic recording or so on. And the science that's addressed here is on time scales and spatial scales and energy scales that are all extremely small. That's what X-rays allow us to do, to go to very fast time scales, to very small spatial scales, and very small energy scales to see small energy differences. So, to make an X-ray laser, what does it take? Why did it take 50 years to go from Charlie's maser and the microwave, and then a few years to get to the optical with the ruby laser, and then 50 years to take to X-ray lasers? Well, for X-rays, we needed an enormous amount of power, and it turned out the only place we can get that is in a particle beam of free electrons. If you like to think about a particle beam with GeV electron energies and milliamps of current, that's megawatts of power for people who think about that kind of unit. So it's a huge amount of power, and it's the only way to make X-ray lasers. So what we need is a curved path. Well, we got a nice one in San Francisco, so we want to make up something that looks like that. And we want all the electrons to be in phase with one another. We want them spaced in a nice uniform way that looks like X-rays. So we don't use this street in San Francisco. We use what's called an undulator, which is a set of periodic magnets. And the bunching of electrons doesn't look like this. It looks like this. If these little dots here are all electrons in a particle beam, and they're normally randomly distributed within a particle beam, if we can force them into bunches where the periodicity in certain relativistically transformed space is at the X-ray wavelength, we can get them to radiate coherently. And that is the essence of the physics of an X-ray laser. Curved paths to make the electrons wiggle. Wiggling electrons is light. And forcing them into bunching at the X-ray wavelength is how to get an X-ray laser out of it. And in a device with magnets here, south-north magnets that makes electrons wiggle, it's those wiggles that allow us to get the light out, which is shown here in red, to build up as the electrons go through this magnetic device, build up, bunch the electrons, emit more light, bunch the electrons more, emit even more light, and then there's exponential growth of the light, and so it looks like a laser. And that's what we're building and what it took 50 years to do. Well, it doesn't sit on a tabletop like Charlie's maser, or in your hand. How big is this? The X-ray laser? Okay, so it starts here 2 kilometers away from where we do the experiments. Okay, you drive over this if you're driving over the freeway. This is down at SLAC at Stanford, and you drive over the freeway here, that's 280. Okay, so 2 kilometers away, you start accelerating electrons, and it takes a long distance, kilometer or so, to accelerate the electrons to high enough energy. And then it takes, you'd have to transfer those electrons into what's called the undulator, which is that magnetic device, and that's 100 meters long. Okay, so again, it does not sit on a tabletop. It's huge. Okay, lots of power, lots of space. And then there are 2 places we do experiments with this now, called the near and experimental and far experimental hall. So overall, it's kilometers of length. Okay, very large. It was, oh, just to show you, so this was proposed 17 years before it was actually demonstrated. So I think another thing to add to your list of important characteristics for discovery is patience. But so what does it look like? Well, if you look down this magnetic device, which is called an undulator because it gently undulates the electrons as they go through the north-south. So if an electron is coming toward you and there are north-south poles of electrons, the electrons will wiggle this way for those students in freshman physics who know about right-hand rules. Electrons wiggle that way, and wiggling electrons wiggle the electric field lines, giving you light. So that's the light you would see, electrons coming toward you. And if we want to change the wavelength of the laser, we change the distance between the magnets like this. Okay, and that can change the wiggles of the electrons, and we get different wavelengths. So this is what it looks like in real space, the 100 meters long of that magnetic device sitting underground at SLAC, 132 meters of these magnetic undulators. And the first day that this actually produced lasing was back in April 15th here last year. And for those of you who actually have played with lasers, the laser jocks in the audience, many of you have known whenever a first laser lasers, it kind of flickers quickly and then it becomes a beam and the spot gets a little brighter. And here we are 50 years later making this laser, and it worked just the same way. So what I'm going to show you on the left-hand side of the screen here is the initial flickering of the laser as more and more undulators were put in. First there were 10 meters of undulator, then 20 meters of undulator, then 30 and 40, and the spot kept getting bigger. The more of the undulators, the longer they put it in. Every once in a while they pop in an attenuator because it got too bright, saturated the camera. But you see that the spot is getting more stable, brighter, and so on, until finally it begins to saturate the output of the laser. So it was making more and more of these poles here. And eventually, if I hit this, the spot looks like this. It looks like a round laser beam. The first thing you do, laser people are very fond of saying, first thing you do when you invent a new laser is shine it on the wall. I think that's what people did with the Ruby laser, is shine it on the wall and see it, and that's what was done here. The output was about a millijoule in energy, but it showed exponential gain like a laser, and it worked pretty much as predicted, which was an amazing feat. This is the control room. Again, is not, it looks more like mission control down for the rocket launches than it does a small laser lab. But the question is, what are we going to do with it? The first thing we're going to do after we shine it on the wall, we have a very powerful beam of X-rays. Took a lot of power to do it, a lot of money to do it, and a very large amount of space. Well, one of the things we can do is use laser light to take pictures, to do photography with coherent X-rays. Well, what does that mean? Well, most of you are familiar with microscopes. Microscopes shine light on an object, and then there's an objective lens forming an image on either a piece of film or your eyeball or something. This is a conventional microscope. And we can do that with X-rays. We can make some X-ray optics to do it, but X-ray optics are really hard to make, and so to use X-rays in a microscope is difficult. So there's another idea, which is to take coherent light and shine it on the material. Take a laser, not a light bulb, and shine it on material, and the light scatters off the sample just like it does in a regular microscope. But we know the laws of physics about how a lens works. Why can't we just collect the light on a camera here that's scattered from the material and do in the computer what the lens might do? In other words, use computer algorithms to pretend, well, to use the laws of physics to say, what would a lens do with that light? It's a little bit more complicated because there's some phasing of the light that's important that the detector doesn't see, but that's a subtlety. But in principle, with modern computers and good cameras, we don't have to have a lens here. We can just collect the light and have a computer do what the lens would do. And that's a much better way to use X-rays because X-ray optics are hard. So what do we want to look at? Well, one of the things we want to look at is proteins in the body. Turns out that using X-rays to understand how proteins, the little machines of your body, function is a very, very important thing, both to our health, to the pharmaceutical industry, to understanding how the body works, how life works. There are all sorts of different protein molecules and so on in your body and other biological materials that we want to understand the structure of. We want to understand these molecules that are maybe 1 million atoms are made up. What is their ball and stick structure? Why do they function as they do? Why does life function as it does? Can we understand it by understanding where all the atoms are? Well, it turns out that X-rays are a great way to find out where all the atoms are. And coherent X-rays and X-ray lasers are an even better way of looking at it. If we have a supermolecule like this, and this might be hemoglobin, something that carries oxygen around through your bloodstream, and the oxygen might be held right in the middle there, like a little baseball glove sitting there, and we want to understand how the superstructure of hemoglobin works, we shine X-rays on it, and we'll get a pattern like this. And the pattern like this can be taken in our computer and essentially Fourier transformed to understand where all the atoms are. And once we understand where the atoms are and how they're moving around, we can understand the dynamics of how hemoglobin works and carries oxygen around in our body. There's another technique for doing it called crystallography, which works as well. But if we can't make a crystal of the protein molecules, what we'll get is a pattern that looks like this. And we'll need a computer to understand it. And the way it'll work is we'll drop the protein molecule into the laser beam will hit it and produce this pattern. The pattern will be collected from maybe 1 million different protein molecules that are all identical and just dropped. Drop, take a picture, drop, take a picture. All the pictures come out like this. Turns out you need about 1 million of them, or somewhere between 10 to the 5 and 10 to the 7 of them. You need to average them, orient them, reconstruct them in the computer and look like this. So this is a grand challenge experiment, which was one of the main reasons the government spent $500 million to make this X-ray laser that I showed you earlier. Okay? It's one of the grand challenge experiments to say, can we understand how all the protein molecules in our body work using a photography technique like this? Now, the problem is, and I'll skip through where it has been, that's been demonstrated to a degree, but not to the degree we need to yet. The problem is that the amount of light you need is so intense that it explodes the protein molecule. There's so much light that it just blows it apart. Okay, but it takes some time. For those of you, again, in physics who know something about inertia, the atoms that might get blown apart don't move instantaneously apart because of inertia. So we want to put the light in faster. And the faster we take the picture, we'll just get its picture before it explodes. Well, the faster we put in the light, that means higher power. It means it explodes faster. We put it in faster. Can you ever win? And the answer, Newton told us, is yes, we can win because of inertia. Okay. However, so the simulation says that if we want to take a picture of this nice protein molecule and we wait for maybe 150 femtoseconds, everything starts to move because we blow it up with so much light on the system. It would be like trying to take your picture with a giant laser. You would explode before, but hopefully you capture the picture before you look like this. That's the goal. Okay, so the key is to look at that, not that. And that means putting in the pulses on time scales which are measured in femtoseconds, which is 1 millionth of a billionth of a second, or 10 to the minus 15 seconds. And the grand challenge we have to do this at SLAC is we'll see how this pays off in the next few years. Another thing to look at is to look at solids. And this is a simulation from Lawrence Livermore Laboratory to say, let's say we don't want to understand biology, we understand some physics. And you know, one of the things that we do in physics is sometimes pound on materials to make them very hard. Remember, that's how they used to make swords very hard, was in an ironworks, was to pound on it. We do this with aircraft wings right now. We peen them with, to make them super hard. And so these are little iron molecules in a box in a computer simulation on a supercomputer. And if we pound on the left-hand side here, we transform the iron from one phase into a different phase. And we create a compressed stage, a different phase, a different arrangement of atoms here than here. If you thought of these atoms as oranges on a grocery shelf, they're arranged in one order here and a different order here, maybe a more random order here. And there are some defects in the material, some places where the oranges are missing. So this is a computer simulation. The question is it true? And the question is, what can we learn about material processing? The only way to understand whether this computer simulation makes any sense or not is to use our X-rays in the same way I just showed you, to take an image to find out where are all the atoms here, where are all the atoms here, and does the simulation work? And we have to do that, again, ultra fast. Sometimes we want to understand how materials blow up. This is where a laser, and this may lead into some of the applications Ed Moses is going to tell us about on fusion, where material is ablated off. This is a copper material which has been heated up on a surface, and blobs of the material fly off and little individual ions fly off. This is, again, a supercomputer, a petascale computer, computing what might happen in physics. The question is, does this bear any resemblance to reality? Hopefully our machine, our X-ray laser, will allow us to image this kind of process and understand whether the computer simulations are right. Other things we want to look at are things that are fast. This is an original photograph from, set of photographs from 1878. Again, happened down at Stanford, taking pictures of a running horse, and the question was, do the horse's hoofs ever, all four, leave the ground at the same time when it's trotting? Okay? No one could look at a horse and see it because things were happening too fast, but if you took a series of photographs, you could see that at some point in the running it actually does happen. So what we want to do is go, here we are, what, 130 years later? We don't want to look at horses anymore, we want to look at atoms moving around. Okay, not horses' hoofs. We go from optical light to X-rays, and we go from milliseconds that are in this time picture to femtoseconds, orders of magnitude leap in both energy of the photons and time. And the way we're going to do that is a future X-ray laser, the next generation, something that I'll be telling you about, showing you pictures of it working maybe in 10 years, because it'll take us another $1 billion in 10 years to build this. Okay, these are long-term devices. We think we can build, again, a long machine here that will produce essentially the equivalent of today's lasers, which are like this laser pointer, but thousands of times more, watts of coherent X-ray power, timescales that are even less than a femtosecond, something called attoseconds, which are 10 to the minus 18 seconds, which is the time it takes an electron to go around in a Bohr orbit around a hydrogen atom. It's about 100 attoseconds. And we need pulses of light that are so fast they can see essentially processes that are consistent with the Bohr orbit time in an atom. Not atoms moving, but electron dynamics in systems. And so on, imaging with nanometer spatial resolution and so on. This is a dream we have. And what we'll look at is we'll look at fundamental processes that happen in nature, like photosynthesis. When a photon of light from the sun hits a leaf and gets converted into energy, into sugars in a leaf, how is it that the quantum mechanics of that all work? How does the energy flow and the information flow around on the leaf? Why is it such an efficient process, and how can we mimic it to make photovoltaics better or to make solar energy conversion? And we think about that as in molecular systems electrons flowing around on energy landscapes of energy systems, and our machine should be able to allow us to watch that. There's combustion work, there's imaging. Right now we're doing some imaging, but of cells, essentially people who know about CT computer tomography or X-ray tomography. If you've ever been had a doctor look inside your chest or so with tomographic imaging to see your organs inside. We can do that with cells, so shrink yourself down all the way to the cellular level and be able to do three-dimensional X-ray tomographic images here of cells. So that this is the nucleus. There's other pieces of material in the cell. We need coherent X-ray light to be able to see this, and we can barely do it now, but we need higher resolution and chemical resolution in the future. So, maybe I'll skip this. This is sort of a summary of what X-ray lasers can do. I'll maybe just sort of summarize here and say what he said in 1958 was the radically new approaches to making shorter wavelength lasers were required. I think we answered that. Took us a while. Particle beams were the answer, the radically new technology. People weren't thinking about that then. That have immense energy density to allow you to get the short wavelengths. Another thing Charlie said is that predicting the applications of laser is, and of course will continue to be difficult. But we still have to have some idea if we're going to convince the government to spend money on projects like this. We have to have some ideas in mind about what to do. And finding all the atoms in biological proteins and understanding their function is one of the goals we've set ourselves if we can build the machine. And finally, fundamental science, of course, stands on the shoulders of giants before us. And so thank you, Charlie, for contributions. And just leave you with a picture of the Bay Area.
So thanks, Roger. We're looking forward to this next generation light source here at Berkeley. So next we're going to have one of our own Cal alumnus, Bob Byer. He was a professor at Stanford and upcoming president of the American Physical Society.
Okay, good. All right. I really appreciate the chance to be here this afternoon and return to my alma mater. I arrived on this campus in the fall of 1960 as a young freshman in the physics department. I almost arrived to take classes in the astronomy department, but I had really good advice from a faculty member at University at Caltech who said, no, young man, you want to major in physics, and if someday in your life you want to be an astronomer, then you can do that. So I followed his advice and followed the path into physics. And fortunately, but you'll see that my interest, by the way, my lifelong interest has been in astronomy. So I'm going to start this talk with what California has done well for the last 130 years. We've been the leader in the world in telescopes, a technology applied to astronomy as a science. The Lick Observatory with 36 inches was the first large telescope in California. Michelson actually used that to warm up for his stellar interferometer experiment. The Mount Wilson telescope and the site, Charlie knows that site well because that's where he set up to do his CO2 laser coherent astronomy and molecular science was in the Mount Wilson site. And finally, the Palomar telescope completed after a horrendous construction in 1948. So we still continue this lead, by the way. We just don't put the telescopes in California, but the design of the 30-meter telescope is being done with Caltech and the University of California. So only a few years after Palomar was completed, Charlie began to think, as he just told us, about how to make coherent amplification of radiation. How do you amplify microwaves using molecules, and how could you possibly amplify light waves using atoms and molecules? So for those students in the audience, I highly recommend you get a copy of this book, Making Waves, and take it and read about a career in science that's worth reading about. By the way, Charlie, Making Waves is the name of a surf store in Hawaii. They sell surfing supplies. That's a very good name. And if you didn't know this little factoid, it turns out the laser business worldwide is about $4 billion of business. It turns out the surfing business worldwide is about $4 million of business. And for those ladies in the audience, the cut flower industry worldwide is also about $4 billion. All right, so we've seen this picture, the concept of the maser. We learned from Charlie directly how the name maser came about. I think it was a great name. It's easy to remember and pronounce. And I like the photograph of Charles Townes with Jim Gordon standing behind the second maser. I just asked Charlie to confirm that this indeed was the second one. He said, yes, of course. We had to build two because we planned to beat them to see how coherent the microwave radiation was. What's interesting about this slide is both men are wearing ties in the laboratory. All right, fundamental science played an important role in Charlie's life, and the word spectroscopy you'll hear again in this talk. And this book, Microwave Spectroscopy, really set the tone for how you can use new sources of coherent radiation to do fundamental science, in this case, the spectroscopy of molecules. And I grew up on this book and on ones related to it in atomic spectroscopy. All right, we move on. From maser to laser, there are very few of us in our scientific career that actually have the opportunity to stand at the threshold of a new area of science, a whole new idea and a whole new pursuit. And Charlie did that twice, not only with the amplification of microwaves, but again with the idea of how to amplify light waves, and which we now call the laser. And again, now you can see telescope in another image. This is a telescope with a yellow beam transmitted in order to correct the image that the atmosphere distorts. And so adaptive optics, an idea first mentioned, I think, by Professor Babcock at Caltech in 1956 or 57, is now a reality. And our ground-based telescopes, including the Keck telescope, use the yellow light from lasers to correct the atmospheric distortion and get much better diffraction-limited images. So lasers in California, again, a lot of the breakthroughs occurred in this state. Ted Maiman at Hughes demonstrated the first ruby laser. The Nobel Prize was awarded 4 years later to Townes and our two Russian colleagues, Prokhorov and Basov. And then starts a whole series of things that involved my career in lasers. So I'll get back to Earl Bell in a second and talk about various aspects of lasers as they have gone on in the last 40 years here in California. But let me note that last year, 2009, was quite a special year. And we'll talk about a 105 kilowatt average power laser. We'll talk about, at the very end, a 4 megajoule infrared laser called NIF. And we're going to have a treat after my talk because Ed Moses is going to give us a 3D fly-through of this laser that you can literally walk in and under. And then we just heard from Roger Falcone that the first coherent X-ray laser was also demonstrated on tax day in 2009. All right, this is my favorite image of a ruby laser. This is Art Shallow, Charlie's brother-in-law, and Art used to do this trick where he would take a ruby laser and buy 2 balloons from the San Francisco City Zoo. One was a blue balloon, it's in the middle, it has Mickey Mouse ears, it's just been exploded, and the other was the clear balloon on the outside. Now the real hard part of this experiment was having enough breath to be able to blow up one balloon inside of another. It is not easy to do that, but Art knew how to do that, and then he would stand here and pull the trigger on his ray gun looking ruby laser and pop. The blue balloon on the inside would pop, and he would say this is really a demonstration of how lasers can be used in medicine, particularly in the idea of laser eye surgery, and his statement, if I had set out to invent a method of reattaching the retina, I would not have invented the laser. All right. I took my wife to see this demonstration when Art was still up and showing at the demonstration. And we sat there and Art pulled the trigger and the ruby laser went bang and nothing happened. So he said, oh, wait a minute, everybody. It's going to take a minute to recharge the laser, pointed the ruby laser again, pulled the trigger, and nothing happened. So he reached in his coat pocket and he pulled out something and he walked over to the balloons and went boom and popped both of them. So he said, you need a backup in case the real idea doesn't work. And so my wife to this day never has seen Art Shallow pull this trick off. All right, I arrived at Berkeley, as I said, in 1960. I was an amateur astronomer. I built my own telescopes. I knew optics well. My first stop was to go visit a young assistant professor named Sumner P. Davis, because I'd read that he was interested in optics, and maybe I could get a job in his lab. And so I knocked on the door, and he looked at me and learned a little bit about me. I was a freshman, remember, and he handed me a book called Practical Spectroscopy. George Harrison was his thesis advisor in the spectroscopy laboratory at MIT. And so Sumner told me, look, go read this book, and when you think you know everything in it, come back and see me. Now that's a pretty tall order for a freshman. So I read the book, and I read it again, and I re-derived the equations. In about May, 6 months later, I thought I was ready to go back and see Sumner Davis. I knocked on his door again in LeConte Hall. He opened the door, handed me a piece of chalk, and invited me to go to the blackboard, and proceeded to ask me to derive the grading equation, and then derive the dispersion of the grading, and talk about plate dispersion, and I managed somehow to get through that. He says, okay, he says, I'll hire you. You're going to take spectroscopy images, and I want you to understand and take the images of the spectrum of lightning in the atmosphere. Now, Sumner wasn't talking about the lightning stroke that we all know about that makes thunder. He was talking about black lightning, the lightning that comes up the positive column before the negative lightning stroke happens. And it turns out it takes hours and hours and hours of exposure to get enough light from the dark lightning in order to expose the photographic plate. But after a couple of years, I was able to do that, and those results were actually published by Professor Loeb in his gaseous electronics book. So Sumner Davis, I really owe him a great deal. He took a young freshman into his lab. I worked with him for 4 years at Berkeley, and during my senior year, Sumner Davis said, look, I recommend you go down and interview at this little company in Mountain View. They're making a thing called a helium neon laser, and maybe they'd have a position for someone like you who's good in the lab and knows a little bit about spectroscopy. So I went down and interviewed. The day I arrived, no one was there to greet me. I sat down and waited in the lobby for about a half an hour. I hear lots of cheering and yelling in the back, so finally I got up and walked around to the back. And here was Earl Bell, and he says, oh, you must be that young kid from Berkeley interviewing for a job. He says, come on in, we'll show you what we have today. And what he had done that day was make the first ion laser, a mercury ion laser that lasers in the orange part of the spectrum. And I decided then and there, this must be an exciting job. So I took the job offer, and then I had to call my fiance, and I had to tell her the bad news. I was not coming to Southern California to work, but I was going to work in Northern California, and I was going to ask her to transfer from UCLA to Berkeley. And that's tough. She did it, and I worked a year at Spectrophysics, a marvelous education on how to make a laser into a commercial product. Tony Siegman held brown bag lunches Wednesdays at noon in the microwave laboratory on campus. So I asked the president of Spectrophysics, Herb Dwight, if I could go to attend these, and he said, sure, but make sure you make up your hours in the afternoon. So I'd ride my bicycle from Mountain View to Berkeley to go sit down with Tony and his graduate students and learn about nonlinear optics, a field that Charlie had a hand in starting. And the two graduate students that attended that, one of them was Jack Marburger, who became president science advisor in the last administration, and the other is John Bjerkholm, who spent his career at Bell Labs working in nonlinear devices. So it was clear to me that there was life after being an undergraduate, and graduate student was a place to go. Charlie, I like the title of Tony's first book, An Introduction to Lasers and Masers. I think that's appropriate because that was right at the transition time when lasers were first coming online. All right, so we did nonlinear optics. I was lucky to be assigned to the Steve Harris Laboratory. Our goal was to build a tunable laser, and the tunable laser that we were trying to build was continuous wave tunable laser. It turns out that the pulsed parametric oscillator had already been demonstrated at Bell Labs by Joe Germain, a student of Charlie's, and Joe is here this afternoon. Thank you for coming, Joe. It's good to see you again. All right, so we made the first tunable CW laser, and we turned it into a commercial product. The company sold about 50 of these tunable lasers, and then went into bankruptcy, which is always a possibility in any small company. Steve Harris, we held a fest for Steve Harris a couple of years ago, and again, his students and former colleagues came back to celebrate his contributions to the area of nonlinear optics. The lasers that we've built in my lab over the last 30 years have all been motivated by scientific applications. Some of them easy, some of them really difficult. And so I use the statement from Edwin Land, don't undertake a project unless it's manifestly important and nearly impossible, as a way of telling my students I expect them to do something quite extraordinary. And indeed, I'll talk about two nearly impossible experiments today. One of them, gravitational waves, which we got into by the back door, and the other one I'll talk about has to do with NIF, as a way we look to the future. So, making light waves, writing light waves, surfing light waves is a takeoff on Charlie's book title. The first tunable laser that we had was in the infrared, and we used it to do molecular spectroscopy in the atmosphere. So this is a spectrum of the molecule carbon monoxide taken in the atmosphere with a tunable laser that can tune across this and do remote sensing. So this field in the early 1970s became a hot field. And in fact, we had international scientists taking part in this, Fumio Inaba and his group in Japan, Sune Swanberg, who is still doing remote sensing with his apparatus in Sweden, and the late Herbert Walter in Germany. So this was quite an international effort to understand how tunable lasers could be used to measure properties of the atmosphere remotely. There's a telescope that we'd put on top our laboratory at Stanford University, and we used it to probe atmospheric temperature and pressure, as well as water vapor and other molecules. In 1984, I met Milton Huffaker, and Milton had a dream that someday the most important remote sensing measurement we could make was to measure the wind velocity on the surface of the Earth from a satellite. That is, do global wind measurements to help us with weather prediction and climate. To date, this nearly impossible task has not yet been accomplished. That is, we have not yet built the satellite and the laser to drive the measurement to do global wind sensing, although it is sorely needed. What it did lead us to is to think about coherent laser radar. Now, radar needs some elements to make radar work, and coherent radar in the visible was not easy. You needed very precise local oscillators. So if you have a challenge, you go after it by inventing what you need. So we invented a thing called a non-planar ring oscillator. We also made a very nice power amplifier, a heterodyne receiver, and we actually sensed wind from our laboratory at Stanford of clouds and the lower atmosphere. This was the key, the non-planar ring oscillator, a very narrow line width little speck of neodymium YAG pumped by a laser diode. The line width when you first turned it on was 10 kilohertz, and if you locked the laser to a resonator, the line width could be controlled down to a microhertz. Quite an amazing little chip of laser gain medium. So that opened the door to all kinds of possibilities beyond remote sensing. And the first one happened. Sometimes in science, things just happen. And while I was visiting the University of Colorado, Peter Bender came up to me and asked me if I could provide him with a laser that would be space qualified, because he was dreaming of an instrument that could measure gravitational waves. And the instrument was an interferometer in space, orbiting the sun, trailing behind the Earth, with a 1 million kilometer path length, a 1 million kilometer interferometer. Quite amazing to think about. And Peter, in his excitement, said, oh, and you know, we're going to launch this in 10 years, so I need your laser before 1998. Well, LISA has yet to be launched, and as far as I know, it will always be launched 10 years into the future from whatever date you're at. So I put 2020 down as a possibility. It turns out gravitational wave astronomy is close to being born. And most of you in the audience, I think, will be here in the 5 to 6 years from now when we actually see this become a field of astronomy. But to make it real, we had to build big interferometers, and Barry Barish and Ray Weiss at Caltech and MIT were in charge of LIGO in the early days. And these interferometers were constructed, 4-kilometer-long vacuum arms, one in Hanford, Washington, one in Livingston. And they're illuminated by a 10-watt laser. The laser, it was a YAG laser designed in our laboratory. And it survived. We designed it to operate for 5 years. It operated well beyond 10 years and provided a very stable, very narrow frequency light source for this interferometer. Has LIGO seen gravitational waves? No, not yet, but we've set upper limits. We're using very precision optics. We're using all the smarts that physicists can imagine to make measurements as close to the quantum noise limit as we can. The ultimate goal is to not only detect gravitational waves in the high frequency range with a ground-based interferometer called LIGO, but ultimately to launch a space-based interferometer called LISA. So now, for those in the audience who haven't thought at all about gravitational waves, I'll give you a very simplified version. Einstein first predicted them from the general theory of relativity, but even he wasn't sold on gravitational waves at the beginning. It took Feynman to actually convince the community that they existed. What are gravitational waves? They're ripples in space-time. They're like a pond of water. When you throw a stone in, the ripples propagate across the surface of the pond. Gravitational waves are ripples in space-time. And if you set a cork out there in the middle of space-time, that cork can move relative to some other reference cork, and you can measure these waves going by. There are a number of potential sources, and we know a lot about the sources now, and we have a list of potential sources that we will see in the next generation interferometer. Our standard candle is either a small pair of black holes that are co-orbiting, or a neutron star binary system that's co-orbiting, and we also know and have seen these in radio and X-ray spectrum, so we know they exist. All right, are gravitational waves strong or are they weak? They turn out to be incredibly weak. And I'll try to give you an idea of how weak they are and why this has been a real challenge. A part in 10 to the 21 is the change of space-time due to gravitational waves. That's one with a lot of zeros after it. And if you think about a distance from our sun to the nearest star, Alpha Centauri, that's 4 light years away, or 10 to the 16 meters of distance, 10 to the 21 times 10 to the 16, a part in 10 to the 21 of a part in 10 to the 16 is 40 microns. Gravitational waves mean that we have to measure the distance to Alpha Centauri to about the diameter of the human hair. This is indeed challenging. It's nearly impossible. We've been trying for 30 years to make this measurement. We have yet to be successful. So Charlie, I'll add one more word to your number of words that we need. We need persistence in this business. You have to be committed to what you're going after and persist if you're going to make it there. There are a number of antennas around the world today, Germany, Italy, Japan, and the United States. And our goal right now that we're working on is to take the initial LIGO that was completed 4 years ago and replace it with an advanced instrument with an order of magnitude more sensitivity. And we're just now beginning to install the parts to make this transition. Once we do that, the volume of space that we monitor goes up by 10 cubed or 1,000. So our event rate goes up by 1,000, and instead of a chance of seeing one gravitational wave every 5 years, we'll be at a point where we'll see a gravitational wave about 1 per week. We know this because radio astronomy and X-ray astronomy has already helped us map out where the sources of gravitational waves are that we can go look for. So that's a nearly impossible science application of a very precision laser oscillator. Let me go back to lasers for a minute. Now this is going to be tough because I wanted to show you another video clip, but the last one wasn't so successful. So let me start by saying one of the interesting things is when you invent things, how do inventions come about? So this is for the students out there. Sometimes you could be teaching a class and a student will ask you a question. So in 1984, I was teaching the laser laboratory course, a graduate level class, and Jeff Dixon and his seatmate Tom Kane asked the question, you know, can you turn a YAG laser, a 1 micron invisible laser, into green so we could see it? And we were studying nonlinear optics in this class, and my answer was, I don't know, but I'll do the calculations this weekend. If you do the calculations this weekend, I'll see you on Tuesday at the next class. That led to the invention of the green laser pointer. Interesting, right? So the green laser pointer is my favorite invention because my hobby is amateur astronomy. And these are used all over the world by amateur astronomers to point to stars in the sky, to point to the objects you want to show people on the sky. And so the green laser pointer is also used as rescue flares for sailors. I would have never thought of that idea. And they're used now in a different color for correcting the images of large telescopes. This is an image of my green laser pointer through my 11-inch telescope in Hawaii. And the green laser pointer propagates rather nicely in the atmosphere. What was the green laser pointer being used to do? Anybody in the audience know this from YouTube? Play with a cat. Yeah, we have a winner. Okay. So the green laser pointer has found another application that I would have never imagined, that cats will chase the laser spot up and down the wall. And again, I invite you, if you type in Hail Stanford Hail onto YouTube, you will find the green laser pointer and you can watch the little video. It's amazing. All right, so our first diode pump solid state laser put out 2 milliwatts of power. Not very much. But this year, and last year actually, the same technology, diode pump solid state laser, put out 100 kilowatts of average power. Now 100 kilowatts is enough power to do, well, let me see, I'll say it can cut metal at a distance. So how did we manage to do this? Well, a lot of thought, a lot of energy went into power scaling lasers. And it turns out a little bit of luck, because you can't make these lasers using ordinary crystals that you grow by this traditional crystal method. You just can't make them big enough. So our colleagues in Japan realized that ceramics could become the laser gain medium. And ceramics that we all know as coffee cup doesn't look very transparent. But if you treat it just right, ceramics can be made to be very transparent. And the one who led the way and convinced us this was going to work was Professor Kenichi Ueda in Tokyo. So here are ceramics. These are YAG ceramics that have been doped with neodymium, and they are indeed more transparent than the best single crystals. More importantly, these ceramic plates can be made in large size, so you can scale the average power of the laser with the area of the slab size. Given that, in the United States, Northrop Grumman Corporation has successfully operated a continuous wave 105 kilowatt YAG laser. It's really an oscillator amplifier, and it runs at about 20% electrical efficiency. And they use adaptive optics to control the laser beam quality, and they coherently add 7 beams to make this 105 kilowatt laser. Why am I leading you down the path of high average power? That's because there's science that can be done at high average power, and you need lasers to be able to do that science. So here's my best guess. Sometime in about 2020 or 2018, we will cross the 1 megawatt average power laser for a solid state diode pump laser, probably at about 30% electrical efficiency. Why am I interested? Because I'm interested in using lasers to drive accelerators to do TeV scale physics. And I need megawatts of laser power to drive accelerators for that type of physics. I'm also interested in telling you about a program called LIFE. And the good news is that the director of the Livermore NIF program is here to show you a tour of what the laser actually looks like. So let me take the last few minutes of my presentation and tell you about the laser at Livermore, and I hope I set the scene so that when the movie comes along, it makes some sense. When the laser was invented, literally no more than weeks later, John Knuckles at Livermore suggested that with a laser, someday you could drive matter to the density and the temperature required to achieve a fusion burn. That is, a laser could be used to make the conditions that exist in the center of a star such that we could generate energy by a fusion burn. So this is a photograph of Art Shallow superimposed on the Shiva laser with his 2 graduate students, former graduate students, PhDs, John Holstrichter and John Emmett. Emmett was director of Livermore Lab for a number of years. So the question is, who invented this crazy idea anyway? This took a lot of patience and a lot of persistence, because ever bigger lasers have been built over the last 30 years, and we're now finally to one that should be big enough to win the prize. So Ed Moses will be up after me. Nice picture, Ed. It must have been taken before you started to build this laser. That's a big laser. So let me see. Ed used to put 3 football fields on top of this laser, but that doesn't make much sense. So I'm going to steal your line, Ed. This is about the size of your friendly neighborhood Walmart store. So just think of a laser that fits in your Walmart store, and that's what this laser is. And all the beams come together at a big sphere right there, a target, and the target contains the small little millimeter scale pellet that has gas in it. So the NIF laser is the world's largest laser. It's the most complex optical system ever built in the world. But now it's running. And it's running because a great deal of care was made in its construction. And all of the glass that's used in this laser is extremely clean, and it's handled in a clean way. And one of the persons that helped all of that happen is in the audience, and that's Mary Spaeth. Good to see you this afternoon, Mary. It was Mary's job to figure out how to keep this glass so clean that it wouldn't damage under the very intense laser radiation. Here are the beams. They're located in bundles. This laser is huge. You walk under, inside, and around this laser. It's of a different scale than we're used to. It was last year when I was in Israel that I got this email from Ed Moses. 1 megajoule barrier breached at NIF. Title of the email. That is, at the UV, the laser had operated above the 1 megajoule level. This was an absolute mind-boggling event. It had taken more than 10 years to get the laser to this point where it runs. On March 15th of last year, this laser was commissioned. That means it met or exceeded all of its design criteria, and I was fortunate to be on the team to walk through and check off the list, item by item, that the laser was indeed ready to be used as a tool to investigate fusion. And what the laser illuminates is a gold hull room. And when the laser light hits this gold, it generates X-rays, and the X-rays do their work. The X-rays then illuminate the outside of this little capsule. It's about 1 millimeter in diameter. The matter streams off of that capsule, creates a rocket reaction. You know that from physics. The capsule compresses and scrunches the gas inside of it down to a small point at extreme pressure and extreme temperature. And the goal is to be extreme enough that you generate neutrons that then burn, and you get a neutron fusion process. So this laser is about a factor of 2 above the threshold for ignition. And the experiments are underway, and I will say that my best guess is sometime late this year, we might indeed run the experiment at NIF, and the team is working really hard to reach this goal, in which fusion in the laboratory will happen. And as Ed likes to say, this would be a sort of a lunar moment. It's one of those kinds of experiments that's been dreamed about for more than 50 years. It might actually happen in 2010. If it happens, we should be prepared to do the next step. And that next step, Ed has aptly named LIFE, laser-induced fusion for energy. And LIFE takes a laser that runs today, 1 shot every 4 hours, and we want to turn it into a laser that runs 5 shots every second. Megajoule lasers at 5 shots a second are 20 megawatts of average power. I walked you up the average power scaling curve carefully so you can understand this is not a pipe dream. This is something that we could engineer today with the commitment to do it. And engineering is underway, not only in the United States, but Kenichi Ueda, whose photograph I showed a while ago, is leading an effort in Asia with the major Asian countries participating. NIF uses glass as the gain medium. The glass was poured in Fremont, California in a continuous pour. It's a great gain medium, but it's hard to make run at high average power. My best guess is we will use ceramics for this laser when it operates at its 5 or 10 hertz repetition rate. So NIF uses flash lamps to pump the gain medium, the same flash lamp technology that pumped the world's first ruby laser. NIF to next generation will use diodes to pump the laser, significantly more efficient so that the laser can operate at high efficiency. So the goal is sometime in the near future, after nearly 50 years of determined effort, we should see, for a brief 10 picosecond duration, a piece of the sun in our laboratory. All right, special year for lasers. 2010, I think, might be a special year for all of us if we can achieve some of these milestones with these high-power laser sources. So 50 years after the invention, it's a pleasure and a privilege to be here and to honor Charlie for his innovative and very thinking about masers and then about lasers. A brief hello from all of the students at Stanford. The OSA group here at Berkeley gets together with the Stanford group for a set of joint activities. And finally, I really owe my family a big thanks, especially my wife, Evie, for allowing me to do what I like to do, which is surf light waves, or in my spare time, surf ocean waves. Thank you.
So that was great. That was a great introduction to our last and final presentation. So this is the Ed Moses from the National Ignition Facility at Lawrence Livermore Laboratories, and he's going to tell us a little more about NIF and show us our 3D movie. So is it time for us to put on our glasses yet, or not quite?
Not yet, Gail. Well,
Not
if
yet.
you want to look at me and not.
So Ed apparently also worked at Hughes for a while, and it's a pleasure to have him here.
Okay. Okay, so I want to start this by talking about how lucky I am not to just be here, but to be the age I am, right? And I was at the age, when I was a child, I was the age of the Mercury program. In first grade, they would take us to the auditorium. It was bigger than this, and they had a 13-inch TV on the stage, and we'd watch it. We couldn't see anything, but we watched it anyway. And that was, I think, actually had a major impact on my life. And then as I got older, I got to deal with computers. The first computers. In fact, for those of you who remember the Bomar brain, I was perfectly at the age for that. But the thing that was most important to me was when I was a freshman, and I saw for the first time in 1967 this. It wasn't a Bob Byer special, but there was a helium neon laser, and it went across the room, and I was so stunned by it. I knew I was going to follow that light beam, literally. And that started me on my way to my laser career. In fact, unlike you, I went to see a Professor George Wolga, who had just come from MIT. And I said to him, Professor Wolga, I'd really like to learn about this. So he said, he reached under his desk and got out a box of parts. And he said, this was the first elliptically pumped ruby laser. Good luck. Right. And I don't think we'd ever do that to students today, but that was the first laser I ever rebuilt. And I learned over time to do a lot of different types of lasers: gas lasers, solid state lasers, liquid lasers. And it's so interesting to me that I come back here, having spent my life building lasers, started off by what Charlie did for all of us. So let me just tell you a little bit more about the NIF. Well, that doesn't look right. It's sort of a big facility, and we heard about it, and it's out at Lawrence Livermore National Laboratory. And this 3 football fields I actually do have a picture of, the game, the famous game on the top, right? Where the trombones are flying and everything. But so it is the Walmart-sized laser. But I think this is sort of an important issue. Even though it's the world's biggest laser, in energy it's about 100 times larger than any other laser that's ever been built. And every single beam of NIF puts out 10 kilojoules in the ultraviolet in the 10 nanosecond regime. So every single beam is the world's most energetic laser of its kind. And because of that, when we put them on these targets, and here is a full-scale target, and I'll talk to you about it more, we can get temperatures of over 100 million Kelvin. In fact, when it starts burning, it goes up to nearly 1 billion. And we can get densities of matter over 100 times that of lead and pressures over 100 billion atmospheres. So we can create conditions that make stars burn, and that we're going to bring star power to Earth. And the long-sought goal of achieving fusion ignition, which is directly traceable to Dr. Townes, directly traceable, and to Mayman's demonstration at Hughes. I actually worked at Hughes. Mary worked at Hughes. A little bit later, is directly traceable to that. And this target is kind of an interesting thing. Is what we do is we put laser energy in, this megajoule plus of laser energy, heat it up to millions of degrees, and build this rocket that we talked about and compress this matter. And I want to show you this movie. So before we look at it, we now get on. And I want you to know how funny you look when I've seen this before. So I'm not going to put it on. I've seen it. But anyway, so this is how this plays. And we're going to start off and look at the laser. And it's 2 laser bays. And first of all, we're going to show the electricity coming into the flash lamps. It's not quite 3D yet. And we just watched the laser, all 192 beams, going back and forth through the system. It's about 1,000 feet. It's a microsecond. Goes to the target, right? Now, if you watch it, you'll see some other stuff. This is, we're going to go in on it and join the laser beams. Now, I'm going to stop it for a second. Or I thought I was going to stop it. And now we're following those laser beams, which are 30 centimeters across, going through the beams. Now remember, it takes a microsecond, so this is quite slow. Speed of light is this. And we're going through some spatial filters that clean up the beam. Does it look 3D? Right. And we're now going to see 48 beams from one laser bay. They're all going together. Pretty soon we're going to see 96 beams from the other cluster. And they're going up to this 10-story building where we go from 2 dimensions to 3 dimensions on the way to the target. Now, it looks like they're not going to get to the target at the same time. They have to get there within a few picoseconds of each other. Through the miracles of modern CAD, watch what happens. Now they're together. They're the wrong color, though. We turn them ultraviolet, and we put them into the target. Now, they're hitting that target within 50 microns each, half the diameter of your hair. I think this looks pretty three-dimensional now, right? And you can see the light coming on. Now nanoseconds are going by, and this target is going up to millions of degrees, around 10 million Fahrenheit, 3 million or so Fahrenheit, Kelvin, and it's blowing off that thing, that gas, and it's compressing it to the temperatures and pressures you need to get fusion burn. Does anyone want to see it again? Yeah. Okay, so let's see what we can do. So let's just play it again. Let's try to play it again. Yeah, I think that might be better in the dark. So that's electric, charging up those flash lamps. Hopefully we'll have those diodes in the future. Now we're going back and forth, heading for that target. So that's the broad picture. Now we're going to look in more detail from the beam line. So we're going back and forth through the glass. By the way, the gain of this is 1,000,000 billion. It goes from nanojoules to megajoules on its path. And we're going to now follow a bundle of beams that's 6 meters long, 20 feet long. That's 20 nanoseconds. And those are 30 centimeters on the side. They're traveling through vacuum now, focusing down so we can clean up some of the spatial noise on them. And as you get into that hole, it seems to be going very fast. So, and now we come back out. Now you can see a cluster of beams, that's 48. Now you're going to see its sister beams in the same bay, 96, going from 2 dimensions to 3 dimensions. That's a 10-story building, so you're watching it go pretty far up and down. And we have some gravitational effects there, the beams going down and going up, right? Changing color slightly. Okay, now we go into, they're going to come all timed up. They time up to actually under 10 picoseconds. And we have to turn their color from sort of infrared to blue. Now they penetrate the target and they heat it up. And let's see if I can do this. So I'm going to just stop it for a second. And you can see this happening right now in real time. And we build this rocket and it all happens. Now, where are we on all this? We're actually doing these experiments all the time. We've done about 170 experiments like this. You can take off your things and come back to this 3D, right? And the thing that's interesting about this is what a real target looks like. And this is how a target looks before it goes in. It sort of looks like a Klingon warship. It has shielding on it. And that's how the light goes in. And by the way, remember, every single one of those beams is pointed to half the diameter of your hair and timed to, a 100th of an inch of light travel time. And there it is in the target chamber. And that always stuns people. The target chamber is 10 meters in diameter, and there it is 1 centimeter. And we have to hit that, very precisely to make that oven work. And I always make fun of this because that arm that's holding the target weighs around 1,000 kilograms or a ton, and the target weighs less than a gram. Only Livermore engineers could do something that silly. But the reason that is we hold it steady to around 10 microns, and that's a cryogenic target, right? So it's running at around 20 degrees Kelvin, and we have to keep it very steady while we're doing it. We have done experiments where we have done that compression. And we're looking at a compressed target with a megajoule of energy onto it. This is around 40 times more than anyone has ever done before. And I want to show you what compression we got. That's what it started at. That's what that little shell looked like when we started it. And that's what it ended. And the fact that it was this round, you know, and this hot was the first major hoop we had to go through in order to prove ignition. And this has been a very exciting last few months doing that. Now is the time for ignition. Now we talk about these long journeys. This is the 50th anniversary of the laser. It's also the 50th anniversary of the idea of ignition. They came almost at the same time. And Dr. Chu, you know, our Secretary Chu, actually, as we know him now, who used to be, you know, the head of LBL and is certainly associated with Stanford and with Bell Labs, now runs the Department of Energy, has had his own transformation about NIF. You know, from being skeptical about it when he was at Stanford, to being interested in it when he was at LBNL, to be owning it now. And, you know, he was out here recently. He wrote, "The National Ignition Facility is a marvel. And while the laboratory will achieve ignition, we hope, we need to think about what we should be doing about it a year or two from today." And then he said, "and for the next 10 years. So the National Academy is going to be looking into, you know, the issue of fusion energy that we were talking about. And our goals are pretty ambitious, you know, and ambitious at a level that some people find almost reckless. I don't. You know, 2010-ish, we get ignition. We think that if there is a will, we know how to build a life engineering prototype, you know, in 2020, and be commercial in 2030, and be a part of a carbon-free environment in 2050. This is a very ambitious thing, but if I think back of the next 40 years compared to the last 50 years, you know, why not? I mean, if you think about where we were, you know, in 1970 on lasers, you know, we were still in the, you know, hardly getting there. Lasers were just starting up. This is the world that I hope we see. And, you know, Charlie Townes started it all up for all of us. You know, I love this picture of this maser. You know, NIF has been a culmination of a long line of glass laser systems, starting from 100 joules. It actually started at lower, you know, then to a kilojoule in the infrared, 10 kilojoules in the infrared, 30 kilojoules in the ultraviolet, and now 2 megajoules coming up in the ultraviolet. This is an incredible journey. As Bob says, but now we have to do this in average power. You know, I think that we know how to do that with people, young people especially, we're going to do that. So I also want to say this is something else we're interested in. Besides going to kilowatts to megawatts, you know, we want to go from petawatts to exawatts, right? You know, I always talk about how the computer crowd is talking about petaflops and they want to go to exaflops. We don't want to be left behind. When you're at the exawatt regime, you can play with the vacuum. You know, you can make particles using this. We will be a part, change the nature of how we explore basic physics. And then, as Roger was talking about, or Professor Falcone was talking about, going from kilovolts to megavolts, you know, get gamma ray light sources. So these are the things that we're all interested in together. So this is my view of the future also. You know, the 50th anniversary of the invention of the laser is here, and 50 years of laser has been great. Thank you, Charlie.
Oh, yeah. Okay. Do you want to do that now? So what do you think? Ed has something he wants to give Charlie, so I guess let's.
Okay, so I was thinking about whether doing this here or dinner, but you know, Charlie, we you know, he was at the NIF, and you know, we had some things. We have some pictures of you here, and we wanted to share everything for you from you know, when you started to what you've done today, and This is a picture of the NIF, and I hope you use it and hang it up somewhere. And thank you for everything. Thank you, Joe. Thank you. Do you want us to hold it and give it to you later? Okay, we'll give it to you later.
So I think I would like to wrap up this session, and we have a reception going on upstairs, and there'll be lots of opportunity to talk to the speakers. There's the exhibits are still up there. Hopefully we still have some of our graduate students here to show off some of the exhibits. And so let's thank all of our speakers again and migrate upstairs.